Unit 5.2, Shear and Moment Diagrams by the Graphical Method. The course outcome we've been focused on in this unit is to demonstrate the ability to calculate normal and shear stress and deflection in beams. In this lesson, our outcome will be to construct shear and bending moment diagrams for beams using the graphical method. Let's review what we covered in the last lesson. Previously, we used the direct equation method to develop functions for internal shear and bending moment in beams, from which we could then draw on a graph. In this lesson, we're going to learn how to draw shear and bending moment diagrams directly from the free body diagram of a beam. To do so, we need to understand the rules for using the graphical method to draw shear and bending moment diagrams. And these rules are described below. If you recall, when we developed functions for shear and bending moment using the direct equation method, we observed that the function for the internal shear is the derivative of the internal moment. That relationship is found in our rules. This rule here shows that the derivative of the moment is equal to the shear. Another way to say that is that the change in our moment diagram between any 2 points is equal to the integral of the shear function between those same points. Another interesting relationship to note is that the derivative of the shear diagram is equal to our distributed load. We could also say that the change in our shear diagram between any 2 points is equal to the integral of the distributed load over those same 2 points. For point loads, we have some additional rules. We get an abrupt jump in our shear diagram wherever we have a point load applied, and that jump is equal to the point load in both magnitude and direction. Similarly, we get an abrupt jump in our moment diagram wherever we have a point moment applied. Now, to understand these rules, it's best to see them in practice. In this lesson, we're going to review several examples where we will put these rules to use to draw shear and bending moment diagrams. For our first example, we have a simply supported beam that is supporting 3 point loads. We have a pin support on the left end, a roller support on the right end. The total length is 20 feet. The first step is to find the reaction forces, which I have already done. Because it's a symmetrical beam, the reaction forces are symmetrical, and they're equal to 15 kips each. Summing the forces in the y direction, we see we have 30 kips pointing upward, 30 down. We're balanced. The next step is to draw the shear diagram directly from the free body diagram. The first rule that we're going to use is shown here. The rule is that there is an abrupt change in our shear diagram that is equal to a point load that is applied, and the jump in our shear diagram is equal to the magnitude of the load and also the direction of the load. Let's start with x equals 0. That is the left side of our beam. And at x equals 0, we have, on our free body diagram, a point load applied. It's the reaction load, equal to 15 kips. So we will see a jump in our shear diagram from 0 up to a value of 15 kips. For the next 5 feet, there are no loads applied. So the internal shear will remain constant at 15 kips. When we get to 5 feet, we have a 10 kip load applied. This will cause our shear diagram to jump downward by 10 kips. We will end up at 5 kips. And because there are no other external loads applied for the next 5 feet, the internal shear force will remain at a positive 5 kips. When we get to 10 feet, we have another 10 kip load applied, so we will jump down 10 kips. From positive 5, we end up at negative 5 kips. We stay constant for the next 5 feet, where we find another point load applied downward 10 kips. That pushes our shear diagram down from negative 5 to negative 15 kips. We remain constant at a negative 15 kips to the end of the beam, where we have our final reaction force equal to 15 kips that will jump us back to 0. We started at 0, we ended at 0. We have confidence we did this correctly. Now we will construct our moment diagram. Our moment diagram is going to start at 0. We can be confident this is correct because we had a pin support at the left end of the beam. A pin cannot transfer a moment, so we would expect the moment to be 0 at the support. The same is true for the roller on the right side. We had a roller support. There is no moment being transferred. So we will only have an abrupt jump in our moment diagram at an end if we have an applied moment or a reaction moment at the end. So we will start at 0. Now the first rule that we're going to use is shown. That is that the derivative of the moment is equal to the shear. Now the derivative of a function will always give us the slope of that function. So the shear diagram is telling us what the slope is on our moment diagram. And we see in our shear diagram for the first 5 feet of our beam that we have a positive 15 kip internal shear force. That means our slope on our moment diagram is going to be positive, and it's going to be at a slope of 15. So let's draw the first 1 foot section of our moment diagram. There will be a line, it will be linear, and the slope of that line is equal to 15. So if we move over 1 foot and our slope is 15 kips, we will end up at 15 kip feet. Another way to look at that is to use this rule here, where the change in our moment is equal to the integral of our shear diagram. So the integral is simply the area under the shear diagram. That is shown by this light blue box. The area under that box is 15 kips tall, 1 foot wide. That's 15 kip feet. So when we move from 0 feet to 1 foot, our change in our moment diagram will be the area under that portion of the shear diagram, which is 15 kip feet. When we move to 2 feet, the area then is 15 kips tall by 2 feet wide. We will see a jump from 0 to 2 feet will be 30 kip feet. And you see we maintain the same slope because from 0 to 5 feet on our shear diagram, the slope is constant. 3 feet, 4 feet, and now at 5 feet, our moment is equal to 75 kip feet. That is the area under the shear diagram. Now, there's something interesting happening now in our shear diagram. We see an abrupt jump. What is that going to do to our moment? Well, now the shear diagram is at 5 kips. That means our slope in our moment diagram is going to change from 15 kips, like we had before, to 5 kips. So if we go over 1 foot, the area now under that section of our shear diagram was 5 kips times 1 foot. That's 5 kip feet. So we will move up an additional 5 kip feet from 75 kip feet to 80. And you see the slope is less steep than it was before. And it will continue at that same slope for the next 5 feet. Now something else interesting happens now at x equals 10 feet. Now the value of our shear diagram is equal to -5 kips. That means the slope on our moment diagram is now going to become negative. When we move to x equals 11 feet, the area under the shear diagram will be -5 kips times 1 foot. That's -5 kip feet, so we will drop from 100 kip feet at the peak down to 95 kip feet. And that will continue at the same slope until we get to x is equal to 15 feet. Here we see then an abrupt change again in our shear diagram. We now have a slope of -15 kips. So we'll see a steeper negative slope in our moment diagram. And if we did it correctly, we will end at 0. And here is our moment diagram. It has a maximum of 100 kip feet. Notice that the maximum moment corresponds to the point of 0 shear in our shear diagram. This is consistent with what we've learned in calculus. If we want to find the local maximum or minimum on a function, we take its derivative and set it equal to 0. Where the derivative equals 0, we get a local maximum or minimum in our function. Here the shear is the derivative of the moment. Where the shear goes to 0, we find a local maximum point on our moment diagram. One other thing to note is that the moment diagram is symmetrical. This will always be true for a symmetrical beam. Let's look at another beam. Here is a simply supported beam with a uniformly distributed load applied. The magnitude of that load is 20 kilonewtons per meter. The length of the beam is 8 meters. The reaction forces at the supports are each 80 kilonewtons. Let's now begin by drawing the shear diagram. The first rule we are going to use is the rule that states that we see an abrupt jump in our shear diagram wherever we find a point load. Here at the end, where x is equal to 0, we have an 80 kilonewton point load applied. So we will see a jump at x equals 0 from 0 up to 80 kilonewtons. Now, the next rule is one we have not yet applied. It states that the derivative of the shear is equal to the distributed load function, or in other words, the slope of the shear diagram is equal to the distributed load function. What this means is that the distributed load indicates what the slope of our shear diagram is going to be. Our distributed load is a load of negative 20 kilonewtons per meter. Remember, downward is negative for our sign convention for distributed load. That means we will see a slope of negative 20 kilonewtons per meter in our shear diagram. So if we move over 1 meter, we will drop 20 kilonewtons, like this. Another way to state this is with this rule here that says a change in our shear diagram is equal to the integral of our distributed load function. And the integral of the distributed load function is just the area under the distributed load. The area is equal to negative 20 kilonewtons per meter times 1 meter wide. That gives us a value of negative 20 kilonewtons. So we get a change in our shear diagram over 1 meter of 20 kilonewtons. Because this distributed load is uniform, it is a constant. So our slope will be constant for the entire beam. Let's see what that looks like. Here at 2 meters, we continue downward an additional 20 kilonewtons. At 4 meters, the area under our distributed load is 20 kilonewtons per meter times 4 meters, that's 80 kilonewtons. So coming down from 0 to 4 meters, our change in our shear diagram is from 80 to 0. And we continue with the same slope until we get to x equals 8 meters. At the end of the beam, we have another 80 kilonewton point load applied that will jump us back to 0 using this rule here. And we start at 0, we end at 0, and our shear diagram is done. Now let's look at the moment diagram. Because we have a pin support at the left side of this beam and no externally applied moment, our moment is going to be 0 at x equals 0. Now here are the rules that we're going to use. We can first talk about the slope of our moment diagram by using this rule that the slope of our moment diagram is equal to our shear. So let's look what the shear is doing. It's positive 80 at x equals 0. And then as we move towards x equals 4 meters, it goes to 0. That means our slope is going to start out positive and steep. And as we move to 4 meters, the slope is going to decrease. And when we get to 4 meters, the slope will be equal to 0, which means it will be horizontal. Now we can use the next rule, which is that the change in moment between any 2 points is equal to the integral of the shear diagram. Let's use that to calculate points on our moment diagram. First, let's look at x equals 1 meter. We can calculate where we will be on our moment diagram by integrating the area under the shear diagram. We integrate it by dividing this area into a triangular piece and a rectangular piece. The area of the triangle is 1/2 times its height, which is 20 kilonewtons, times its width, 1 meter. The area of the rectangle is 60 kilonewtons tall, 1 meter wide, and together that equals 70 kilonewton meters. So that's this value here. Notice the shape of this line. Because this is a linear function for our shear diagram, we are going to have a quadratic function for our moment. So this is going to end up looking like a parabola. Now, when we move to x equals 2 meters, the area underneath the shear diagram from 0 to 2 meters can be calculated as 120 kilonewton meters. At 3 meters, and then when we get to 4 meters, our slope we see on our shear diagram has gone to 0. And the value under the shear diagram is this triangle here in blue. Its area is 160 kilonewton meters. That is the peak point on our moment diagram. Continuing on from the midpoint, because our shear diagram is negative, we will see a negative slope in our moment diagram. And if we've done it correctly, when we calculate the entire area under the shear diagram, we will end up with a moment of 0. And that is our moment diagram for the beam. Notice, as we saw before, the moment is 0 at the ends and maximum where the shear is equal to 0. In a symmetrical beam like this one and in the previous one, the maximum moment is right in the middle, and the shear was 0 right in the middle. That's no coincidence. The next beam we will consider is simply supported with a point moment of 20 kilonewton meters acting at the midpoint. The direction of the moment is in the clockwise direction. Because the loading is unsymmetrical, the reaction forces will also be unsymmetrical. First, we begin by drawing a free body diagram. Summing moments about point A, we can calculate the reaction force at B, which is equal to 2 kilonewtons. Positive, which means we drew our arrow correctly here. Now, summing forces in the y direction to solve for our reaction force at A, we can calculate that it is negative 2 kilonewtons. So I've drawn my arrow the wrong direction. Now we'll draw the shear and bending moment diagrams. We will begin with this rule, which is that we have an abrupt jump in our shear diagram equal to a point load. So right here at x equals 0, we see a jump down to negative 2 kilonewtons. We remain constant over the next 5 meters. Now at this point, we see we have a point moment applied. What does that point moment do to our shear diagram? Well, the answer is it does nothing. We continue straight through at a constant negative 2 kilonewtons till we get to the right side of the beam where we have a reaction force of 2 kilonewtons that bumps us back to 0. Now we draw our moment diagram. Because we have a pin connection at the left end, our moment diagram will start at 0. And using this rule here, which says that the shear diagram is the slope of the moment diagram, we see that our shear diagram is at a negative 2 kilonewtons for the entire length. That means our slope on our moment diagram will always be in the negative direction. Because we have a roller support at the right end of the beam, we know we were going to end with a moment of 0. So we're going to start at 0, end at 0, but we have a negative slope always in between. Let's see what this is going to look like. For the first 5 meters, our slope will be at negative 2, so we will proceed from 0 down to a negative 10 kilonewton meters. Using this rule, which states that the change in our moment diagram between 2 points is equal to the integral of the shear diagram between those same 2 points. We see that the area from x equals 0 to 5 meters is negative 2 kilonewtons times 5 meters, that's negative 10 kilonewton meters. That's the change we see in our moment diagram. Because our moment diagram will end at 0 and the slope will continue at a negative 2, something must happen right here at the midpoint of the beam where that point moment is applied. And we are going to use this rule here, which states that the change in the moment diagram is equal to the applied point moment. So we're going to get an abrupt jump in our moment diagram equal to the magnitude of that moment. It is 20 kilonewton meters, and we are going to jump up 20 kilonewton meters from negative 10 up to positive 10. And now, as we proceed along the beam, we will continue at a slope of negative 2 kilonewtons, and over the next 5 meters, we will close back to 0. There's an important rule that we need to discuss here, which is that when we have a moment applied in the clockwise direction, we get a positive jump in our moment diagram. When we have a moment applied in the counterclockwise direction, we get a negative jump in our moment diagram. This rule can be remembered by drawing a free body diagram of the beam with a point moment applied. You can see if this is a point moment is applied on this beam in the clockwise direction, then the support reaction on the right will be pointing upward, and the support reaction on the left will be pointing downward. As if you were to grab this beam and twist it in this direction, it would push this end in the ground, so the support would have to push back. And if you twisted this beam, it would try to lift this end, so the support would have to hold it back. So that helps us understand the direction of our reaction forces. Plot the shear diagram, we see that it is going to be negative for the whole distance. That means our slope is negative, which means if we're going to start at 0 and end at 0, we must have an upward jump at the point where the moment is applied. In the beam on the right, draw a free body diagram with the moment now going in the counterclockwise direction. You see that will switch our reaction forces, so our shear diagram will be positive for the entire length of the beam, which means we have a positive slope in our moment diagram. This means we must jump downward at the point where the point moment is applied. And we're done.